Okay, everyone, we're very happy to have Jordan Cotler from Harvard today. He's going to tell us a bit about exact RG and the relationship to optimal transport.
Well, thank you so much for giving me the chance to speak about this. And sorry that I couldn't be there with you guys in person, but hopefully we'll have a chance to visit soon. Make it to Chicago pretty often, since I grew up around there. And today I'm going to tell you about some work in collaboration with Simone that came out earlier this year. And the subject of the talk is the renormalization group flow as optimal transport. And I'll talk precisely what I mean about RG flow, as well as the subject of optimal transport, which I suspect is probably a bit less familiar to the audience of high energy physicists. So let's begin with a bit of an overview of the renormalization group at a very high level. So the basic question which the renormalization group addresses is, how does our effective description of a physical system change as we tune the precision of our measurement apparatus? Now, the renormalization group is one of the central engines of quantum field theory and statistical field theory, and is essential to holography. The question that we're going to address, or rather attempt to address in this talk, is what does the renormalization group really mean, either computationally or information theoretically? That is, by recasting the renormalization group into a different kind of language involving information theory and optimal transport, we can bring to bear the tools of these subjects to inform us in a more deep way as to what the renormalization group really means, and allow us to discover new properties, which were not previously known, as well as new algorithms for computing RG flows in practice. So again, this is the subject of the talk. I should also say, of course, feel free to ask any questions throughout, either the people attending over Zoom, of course, or in person. So here's the basic setup. Suppose for now that we have a Euclidean scalar field theory on RD. So that is, we have a scalar field that maps RD to R. And we have an associated probability functional that corresponds to this Euclidean theory. I'll call it P sub lambda of phi.
Sorry, Jordan, to interrupt you, but is there any chance, our system's on max volume, but we can't hear you very well. Is there any chance your mic might be able to, if there's any tuning on your side, perhaps not, but.
Let's see here.
Is it full on the computer as well? Yeah.
Coming through fine over Zoom.
But you
Fine over Zoom, yeah.
Well, I think. Where's that?
Good question.
It's like in the top right, in the top right Mac.
Okay, sorry, maybe it's on our end. We'll try to.
Yeah. Well, we could also mute. You could, in the worst case, you can always mute it when someone asks a question. You can unmute it or something. Okay. Well, anyway, perhaps I'll continue, but let me know if there are further difficulties. We can troubleshoot.
Yeah, go for it. Sorry about that.
Oh no worries. Of course. So we have a probability functional P sub lambda of phi, which is proportional to e to the minus s sub lambda of phi, where our RG scale, or maybe I should say our cutoff scale, is lambda. We can regard this as the highest momentum scale that we can access, or conversely, 1 over lambda is like L, which is the shortest length scale that we can measure. And we can regard S sub lambda as our effective action that governs the physics that we can access at up to momentum scale lambda. Now, the exact renormalization group.
Sorry, is S sub lambda a local functional?
Not necessarily. In general, not necessarily. Although what we will often do is that we will stipulate that at some initial point where we are going to start the flow, that it is going to start off as being a local functional, but as we perform the flow, it could become progressively more non-local.
But so then, if you don't truncate, then you're not really doing anything effective. You're just doing the path integral in steps.
That's right. Well, we're going to be interested in understanding a framework for thinking about how to do the path integral in steps or in a non-perturbative way, and we can truncate later on. In other words, what we're going to be interested. So one thing that you could do is that at each infinitesimal step at RG flow, you could truncate it, or you could do the exact flow and truncate it after. We're going to be interested in what happens when we do the exact flow, and if we would like to truncate it after. But we're going to just be interested in understanding structural properties of what the flow looks like in the exact sense. And we could talk later about why this is an interesting question, or why it is that we wouldn't want to truncate it at the outset. So we have the exact renormalization group flow. So the idea behind this is that as we as actually was just being asked, the usual thing that we do is that we truncate it so that we have a local or quasi-local effective potential. But in fact, there is a way of non-perturbatively understanding what the exact renormalization group flow is, namely the exact path integral answer for integrating out momentum modes. And structurally, these kinds of equations have the following form. If we take the logarithmic derivative with respect to the scale, or if we take a derivative in scale with respect to p sub lambda of phi, so we see how its scale dependence changes by an infinitesimal amount, then on the right-hand side, we can write some functional equation in terms of p and its first few functional derivatives, usually up to the first two functional derivatives, such that this flow equation ends up corresponding to an exact RG flow corresponding to some particular choice of scheme, namely some particular RG scheme, which actually specifies the choice of this F. And we'll give some examples of this shortly. Now, this type of exact RG flow equation was developed by Wilson, and there's a nice review by Wilson and Kogut in '74. I believe Kogut typed up the lecture notes of Wilson, but also in particular in the work of Polchinski in '84, who really nailed down and had a beautiful characterization of a particularly nice exact renormalization group flow equation, which we'll discuss in detail. What we're going to show in this talk is that for a broad class of exact renormalization group flow equations, including Polchinski's, but also a much broader class that practitioners in this subject use in practice, that the exact renormalization group flow equations can be written in the following form. So let's unpack what this means. So here we see that the derivative, again, of the probability function with respect to scale is equal to minus the gradient of a relative entropy between p sub lambda, which is the distribution that we are going to flow, and some background distribution q sub lambda. Here, this is a derivative on the space of probability functionals. So it's a derivative on an infinite dimensional space. To define a gradient, we need to do it with respect to some metric. And this metric is one which is on the space of probability functionals, which we'll have more to say about shortly. And this gradient is with respect to a metric which is called the Wasserstein-2 metric, which is going to be related to the theory of optimal transport. So this is a metric with very beautiful properties, and its gradient, the associated gradient, has very interesting properties, which we'll explore in some detail. This S is a relative entropy between P sub lambda, which is the distribution which we are flowing, and some background distribution Q sub lambda. This background distribution can be regarded as a prior in the language of, say, Bayesian inference, but we can regard it as indicating a choice of scheme. In particular, if we change the choice of background distribution Q, then this corresponds to a different scheme by which we are coarse graining or performing RG flow. And the punchline of this equation at some structural level is that the renormalization group, the exact renormalization group, is equivalent to an optimal transport gradient flow. The optimal transport is related to the properties of this Wasserstein-2 metric, and it's a gradient flow because of the structure of this equation of the gradient, which is appearing on the right-hand side, acting on the relative entropy. Now, the talk is going to be divided into 5 parts. In the first part of the talk, I'm going to review the exact renormalization group, as well as the theory of optimal transport, with an emphasis on the latter, because it's particularly interesting, and as I said, something which is not presently known, or at least known to most practitioners of high-energy theory. In the second part of the talk, I will explain this boxed equation from the previous slide, namely how the renormalization group with the exact renormalization group can be recast as an optimal transport gradient flow. In the third part of the talk, I will explain how this particular structure of the equation allows us to derive or to infer new RG monotones, which in fact have a non-perturbative derivation using formal properties of the path integral. In part 4, I'll discuss how this formulation of the renormalization group flow enables a new variational formulation of RG. Namely, that if you would like to do a single step of RG or perform RG flow by a certain amount, you can cast this as a certain kind of minimization problem, which is extremely useful or which has a lot of promise for certain kinds of numerical and maybe other conceptual applications. And then in the last part of the talk, I'll terminate with a discussion of what this all means, as well as where to go, how to go proceed forward. So let's begin with a review of the exact renormalization group flow and the theory of optimal transport. So let's begin with the exact renormalization group flow, and I'm going to focus for the moment on the simplest instantiation of it, or one of the nicest instantiations of this subject, due to Polchinski and his seminal paper on the subject in 1984. So suppose that, for simplicity, we have Euclidean scalar field with a source. So here we have, let's suppose that we start with some initial quadratic term. We have this is the usual quadratic term for massive scalar field. We have our kinetic term and our mass squared term. And here we have a kernel, which so k sub lambda of p squared is a cutoff function, which starts off at 1, and for scales above p being the cutoff scale lambda, this function smoothly goes to 0. Now, by k inverse, I just simply mean the reciprocal of k sub lambda. So k inverse is just 1 over k sub lambda. Now, the reason that this is present is because when we compute correlation functions, when we bring down, for example, factors of the propagator downstairs, by Wick's rule, for instance, this will have the effect of bringing down k sub lambdas, which are going to smoothly cut off the correlation functions in the theory. Now, this j of p is going to be our source. This is the source appearing in the partition function. And let's assume for the moment that the source vanishes above the cutoff scale. So we're only going to be able to probe physics below the cutoff scale using this source. And finally, we have an interaction term, which I'm not going to specify at the moment. So here we see that, at least initially, I've specified the dependence of the quadratic terms on the scale lambda, but I'm not yet going to specify the dependence of the interaction terms on the scale lambda. We will leave that to be determined in a moment. So the basic insight of Polchinski is that the physics below the cutoff scale is preserved under RG flow. That is, if our source J is only accessing physics sufficiently below the cutoff scale, for example, if J smoothly goes to 0 at and above the cutoff scale, then it's the case that if we take a derivative with respect to scale of the partition function, then it should only change the partition function up to an overall multiplicative constant c sub lambda, which does not depend on J. What this means is that the correlation functions that we can compute by taking functional derivatives of J are unchanged by changing lambda by a little bit if J is only accessing physics that are sufficiently below the cutoff scale. And of course, because of the way the fact that the partition function only encodes the physics up to a multiplicative constant, we are allowed to have it change by a multiplicative constant c sub lambda as we change the scale, or at least this is a.
Sorry, is this equation true like for p as some kind of series in p squared over lambda? I'm a bit confused about the mixing of the phrase exact with the fact that you're talking about small momentum and you have a kind of arbitrary function here. Can you add a little more?
There's no notion here of small momentum. The only assumptions that we would like to make for this is that there's a cutoff scale lambda, and that there is a kernel which decays smoothly to 0 at around p squared equals lambda. But the thing which is essential for this argument is that the j's, so say for simplicity, the j's go to 0, exactly to 0, before they reach the cutoff scale, before they reach lambda. So the j's are compactly supported for, say, the norm of p less than, say, lambda minus epsilon. That's sufficient.
Okay, but if I probe correlation functions of momentum slightly less than lambda, won't I see the effect of this k?
Yes, you will.
So therefore, I don't understand. I mean, I'm a bit confused about that.
But the effect of k is a different question than computing correlation functions. The point is that if you okay, so the point is that if you suppose that that J, that our source, dies to 0, say at lambda minus 0.5 or something like this. So what I'm saying is that if I change the scale by an amount which is less than 0.5, say by an infinitesimal amount, I'm just taking a derivative here, then the J correlations will be unaffected by this, because J doesn't see things that are very, very close to scale lambda. It just, you can't probe that.
Are you sure that that statement is true no matter what k is? Like, what if k is not exactly 1 there?
It shouldn't matter, because
it shouldn't matter asymptotically for low momentum, but I don't see why it doesn't matter as an exact statement.
How do I say? It's simply because, so think of it this way. If you compute correlation functions with respect to J, and then you do a little bit more of the path integral that doesn't, how do I say, if you integrate out some more momentum degrees of freedom that are not going to touch whatever is coupled to J, namely the only degrees of freedom which are coupled to J are those up to lambda minus 0.1. Okay. The point is that if you perform a bit more of the path integral that just doesn't touch the degrees of freedom that are coupled to J, then it's not going to affect the answer that you get for the correlation functions, even if you have a K dependence which smoothly goes to 0.
It's because you ask that the boxed equation hold that is the basis of deriving the exact renormalization group equation. So it's not like, you know, it's an assumption. It's a request that the partition function and the correlation functions have this property, and a consequence of that request is the exact renormalization group equation.
So maybe to say it this way, so maybe another way of rephrasing that is that this corresponds to a family of very reasonable RG schemes. Or is a family of RG schemes which should satisfy this property, which for which those are going to be the ones that we're going to consider. We could consider others, I suppose, that have other behavior which do not satisfy this property, but this is a reasonable condition for a reasonable way in which the partition function can behave as we change scale.
Maybe Clay's asking how this can be exact if K is smooth without some very small correction.
Let me show you. So so how do I say? So let me maybe address this one in like 2 minutes, because let's see, for example, if there is a way in which we can solve this set of equations, which will give us a reasonable answer, then we can post facto decide if we got something that was reasonable or interesting. So the idea is that if we write this particular equation, if we write the left-hand side of the equation, we expand it out. So I'm just expanding out the left-hand side. We see that if we would like this start equation to hold, then it's the case that we would like to, one way that we can arrange for this is by choosing some clever ansatz for the way in which the interaction terms change as a function of scale. So there's a kind of Jeopardy question which Polchinski asks, which is there a functional differential equation for this quantity, namely the interaction terms as a function of scale, such that the start equation is satisfied? And one solution to this is not the unique solution, but a solution to this is what is called the Polchinski equation. That if we take the interaction term and it satisfies this functional differential equation, if we take a derivative with respect to scale on the right-hand side is equal to this kernel smeared against two functional derivatives of the sort of quadratic combination of the interaction terms, then by plugging this back into this expression, this will end up reducing to a multiplicative constant times e sub lambda of j. So in other words, this is a particular solution to the way in which the interaction terms can change such that this start equation is satisfied. It is not a unique solution to this. There are other ways of doing this, but this corresponds to a particularly nice choice of scheme whose properties we'll discuss in a little bit, which was what Polchinski ansatzed or derived. And again, maybe as we were suggesting, there are other kinds of schemes in which the start condition does not hold, but for the purposes of this talk, we'll be interested in those schemes for which the start condition will hold. Now, let me make a comment about the Polchinski equation, is that it has been long known, let me rewrite the Polchinski equation in a slightly different form. I'm going to write it not in terms of how the interaction term changes, but how the full probability functional changes. Then the way that it changes is in terms of this functional differential equation, two derivatives acting on phi here and one derivative acting on, on p, and so two derivatives acting on p, and here there's another term with a single derivative acting on p. If I compress the notation a bit, if I absorb some of the kernels into this other kernel c sub lambda, then we can see that this actually has the form of a convection diffusion equation, where here we should associate t, the time parameter, is being associated with minus log of lambda, where lambda is our scale. So we see here that here we have this quadratic term in phi, which maps onto schematically onto this term. And we have this term here in which This is like a convection type. And we see that here this index contraction, I and I, is here replaced with a continuous index contraction, namely this integral over P. So it has been known for a long time the Polchinski equation can be thought of as a type of convection diffusion equation. And there's something which is kind of intuitively nice about this that people have pointed out before, at least at some high level, which is that in a diffusion equation, we expect that a diffusion equation is one in which entropy increases along the, as a function of time. And there's a sense in which in the Polchinski equation, as we perform some kind of exact renormalization group flow, some entropy which is associated with the probability functional is also, insofar as it is well defined, suspected to also be monotone under the flow. Or at least this is intuition that people have stated in the past, which we will attempt to make much more precise in a little bit. Now, there's a more general framework for understanding exact renormalization group flow, namely called the Wegner-Morris flow equation. So recall that I showed you this starred condition that we were talking about, which picks out a particular family of exact renormalization group flows, and I stated that the Polchinski equation was one particular solution, or one particular way of satisfying that equation, but was not the unique way of doing so. There's a much broader family of solutions to that starred condition, which are given by the Wegner-Morris flow equation, which reproduce the Polchinski equation as a special case. Now, the Wegner-Morris flow equation has a different form, but also suggests a different interpretation of how to think about renormalization group flow. It was the first parts of it were originally written down by Wegner in '74, but it was clarified in a substantial way by Morris in the mid-90s, and also developed by him and his collaborators in the first decade of the 2000s. So here's the basic interpretation. What this equation does is that it's inducing a reparametrization of phi. That an infinitesimal step of this equation in scale is mapping phi to a phi prime, which is related to the original phi, by delta lambda over lambda times this object psi, which is called the reparametrization kernel. So what this does is that as we change by an infinitesimal amount of scale, it changes the probability functional by a reparametrization. So it maps phi to phi prime, and then we also have a Jacobian factor out front. Here's a way of thinking about what this means. So suppose that in a simpler situation that we have a probability distribution not on the space of fields, but on, say, the real line. We have a smooth probability distribution with support over the real line, like a Gaussian distribution. As we change the distribution by a little bit, for example, suppose we're doing something like heat flow or some other kind of equation where it smoothly deforms, we can actually think about an infinitesimal step of the flow on that probability distribution as being instantiated by an infinitesimal reparametrization of, say, the real line. That by a parameterization, we deform the probability distribution into the new one, undergoing a particular step of, after a particular infinitesimal step of the flow. What the Wegner-Morris flow equation does is that it repackages the data of the renormalization group flow into that of a reparametrization on the space of fields, which induces a reparametrization on the space of probability functionals on the space of fields. Now, this you can regard as a type of nonlinear vector flow type equation, where again, t is associated with minus log lambda. We are flowing p by a vector field, which can depend, in fact, on the probability distribution itself, as well as on as well as on x, which in this case would be on the fields. It has some dependence on the fields. So there is, in fact, a characterization by Wegner of what is a nice class of reparametrizations, these psis, which should correspond to sensible RG schemes that have some sense of locality in position space or have reasonable properties of momentum space. And there's some partial characterization of what different suitable reparameterization kernels psi should look like that give features that we would associate with reasonable RG flow schemes. Now, I just would like to make a point. These equations are not particularly important, but I'm going to maybe skip through them in the interest of time. I just would like to observe that the Polchinski equation can in fact be written in this form for a particular choice of this reparameterization kernel. And maybe it's not at the moment so useful to stare too deep into these equations, but there is a way of casting it into this. But the point is that this set of equations actually characterizes a much larger class of exact renormalization group flow equations. So now let me tell you a little bit about the subject of optimal transport, which we're going to.
So I didn't understand. Can you
of course
go back? So the exact normalization group flow equation, these different solutions, Is there some physical principle that tells us which is the solution that we want?
So the idea is that if you have, say for Euclidean theory, a particular choice of RG scheme, which we usually define perturbatively, namely using perturbative methods, you can try to find, for example, a exact RG scheme which agrees with your particular RG scheme that you're doing infinitesimally perturbatively. So you can find, for example, if you will, a non-perturbative version of some infinitesimal scheme of your choice. But in particular, just as with anything else in RG, there are many different viable schemes or different viable ways of doing coarse graining in the path integral or integrating out degrees of freedom. And these psis roughly characterize or provide a different way of formulating what those ways are in which we can integrate out degrees of freedom in the path integral. In a manner which is kind of local in momentum space to a particular, it just generalizes what it means to do coarse graining in the context of the path integral is the short of it. Is that, I'm not sure if that's exactly what you were asking me.
Well, maybe. I think you're saying that all the different solutions are just some non-perturbative definitions of different schemes. Though which class of schemes you can access this way is not obvious.
That's true, although in practice, what people have done in this subject is that they've taken a lot of different standard schemes that people use in the literature, such as maybe, the ones that you would learn in, a standard textbook in statistical mechanics, and have found completions of them which fit in this form. So in other words, the reason why this Wegner-Morris flow equation is often used is because it captures essentially almost all of the schemes that people use in practice, namely non-perturbative versions of the perturbative schemes that people use in practice. So that's why, that's sort of why people are interested in this particular flow equation. It's because it does capture this non-perturbative versions of the standard perturbative things.
So, I mean, usually I think that different choices of scheme are parameterized by different choices of local counter terms, but I don't see that here. So that's why I'm having a hard time with the answer that you're giving.
Well, so let's talk about a particular example to show you why. I mean, I think that the thing you're talking about of different choices of local counter terms is, I mean, it depends whether you're thinking about this in a perturbative or
no, no, that's a non-perturbative statement. That's just saying that schemes differ by contact terms and correlation functions.
Sure, but so let's consider the following thing. So suppose that our RG scheme, I mean, this is particularly, since this is the Kadanoff seminar, we can do, let me give you a large class of RG schemes which are related to Kadanoff block spin renormalization. What you can do is that you can replace, you can put, say, a delta functional or a delta functional into the path integral, which replaces, say, phi of x by, how do I say? So you can have another field, say, call it psi, which is related to phi of x by taking phi of x and convolving it with a smooth kernel. So in other words, this is a particular way of coarse graining. It's sort of like a continuous version of Kadanoff block spin renormalization, where you take all the fields and you convolve them with some kernel. And there should be a way of you can phrase this in many different languages, but there's clearly an infinite number of ways of doing that, which are contingent on the kernel by which you are smoothing the field-theoretic degrees of freedom, namely the fields. And you could talk about it in the way that you're discussing it, but there's a particularly clean way of talking about this in terms of the Wegner-Morris flow and a host of other different ways of coarse graining as well.
Can I say, oh, great, this is great. I think what you're really getting at, what this explanation is useful for, is what's really at the core of a lot of people's confusion of what how to understand renormalization group flow. And it's the point which you're making very nicely with the talk about reparameterization invariance. The point is that the physics doesn't change, so you change perturbatively, you change your description in terms of values of couplings, right? And I think it's very easy to get confused on those seemingly sort of opposite goals, but yeah, being clear that it's really reparameterization invariance seems like a really useful explanation thereof.
I agree. I really like this perspective, and I should say the paper which articulates that point in the cleanest possible way is a paper by Morris and Latour from the late 90s or early 2000s. They have, I would recommend this paper if people haven't looked at it. It's just, it really exposits what is essential about this equation, how it relates to the more usual perspective of RG flow. But maybe in the interest of time, let's maybe table this for now and we can come back to it. And let me tell you a bit about optimal transport. So it's unusual in a physics talk to be able to, in earnest, cite a paper from 1781 or a work from 1781. But in fact, that is appropriate to do so, the work of Monge and the later work of Kantorovich in 1939. So let me give you the basic question of the optimal transport problem as Monge saw it at the time. So suppose that you are in a battlefield and there is a large number of mounds of dirt. And what you desire to do is that you have a desired configuration for the mounds of dirt, which is different than the current configuration. And you have a shovel and you want to, bit by bit, you would like to reconfigure the piles of dirt as you have it into the desired configuration. And your question is, how should you do this while expending the least amount of energy possible? So here is a bad way of doing it. A bad way of doing it is to take all of the dirt and the different piles, to aggregate it into a single pile, and then to reallocate it into the desired configuration. That seems like it would cost more work than just simply, in a more clever way, kind of piecemeal reallocating the existing piles into the new piles without having to consolidate them into a large pile first. So you can imagine that for practical reasons, so Monge was very interested in this set of questions in the context of helping the French military, and in particular was actually instrumental in various aspects of the French Revolution thereafter. And he was interested in also transporting artillery and various other kinds of questions related to that. Kantorovich was also interested in the more military applications of these questions in the wake of World War II. Although he had a slightly better mathematical formulation, which I'll explain shortly. But in any case, this optimal transport is sometimes called the subject of the earth mover distance for the reason that I said, in this very literally down to earth way of thinking about the problem. So let's formalize it in some more mathematical terms. Suppose that we have two distributions. We have P and we have Q, which are distributions. I've shown them on the real line, but you can put them on any space you want. Let's call the space X. So we have an initial and final distribution, P of X and Q of X. This is our initial configuration of dirt, say, and this is the final configuration which we so desire to configure into. We have a transport map, which is say a diffeomorphism from X to X. In this case, in this picture, X is just the real line, which has the property that the push forward of P under the transport map is equal to Q. That is, if we perform this diffeomorphism, then we will have successfully turned the P distribution into the Q distribution. We also have a cost function, which is a map from X cross X to the real line. And the way you should think about this is it's the cost of taking an infinitesimal amount of dirt from one point and moving it to another point. So in other words, the first X here is the location of where the dirt starts. The second X corresponds to the position of where the dirt ends, and R is like the cost of moving it from one place to another. So then the total cost incurred by this is the integral over the space, again, of dx px of the cost function of taking a piece of dirt at X and bringing it to T of X, where the initial distribution is P of X. So this is called the Monge functional. And the idea of the optimal transport problem is to minimize the total exerted cost over the space of transport functions which satisfied this property that the push forward of P under T is equal to Q. So you minimize this functional with respect to T that satisfy this constraint. That is Monge's formulation, or a modern interpretation of his formulation of the problem. Now, let me give you a different formulation of the problem, which is a bit cleaner due to Kantorovich, which is, in a certain sense, the modern formulation, or the one that's most often used. It starts with the same basic ingredients. We have an initial and final distributions P of X and Q of X, and we have a transport kernel, which is pi of xy, which tells you the amount of dirt, if you will, or the amount of probability mass that you transport from position X to position Y. it has the feature that if you marginalize the second coordinate, then you recover P of X. And if you marginalize the first coordinate, you get Q of Y. So in other words, you can think of pi of xy as a joint distribution over two copies of the space x cross x, which marginalizes to P on one of the spaces and marginalizes to Q on the other space. And we also have our cost function here. And now the total cost takes this very simple form where it's just the integral over x and y of pi of xy, the amount of dirt that we're transporting from x to y, times the cost of doing so, c of x to x and y. Now, the utility of this particular formulation is that it's a relaxation of the Monge problem, which means the following thing. It means that there are certain P's and Q's which do not have a solution in the Monge formulation, but which do have a solution in the Kantorovich formulation. So there are generally, the Kantorovich is more flexible and provides you with solution to a broader class of problems. So just to tell you an example, suppose that the P distribution, for instance, is two delta functions, and the Q distribution is a single delta function. Then there is no solution to the Monge formulation, but there is a solution in the Kantorovich formulation. It has to do with the fact that the probability distributions having disjoint supports can be problematic at the Monge formulation. So in the Kantorovich formulation, there is a particular notion of distance called the Wasserstein distance, which was actually not due to Wasserstein originally, but was due to Kantorovich, but it has been named Wasserstein ever since, so we will use that name. The Wasserstein Q distance corresponds to letting C be the distance squared between the 2 points, x and y, and is the infimum over pi in this set gamma of PQ. This simply means the set of pi that marginalize to P on this, to P and Q respectively on the different spaces. So this is just performing this minimization over pi with respect to this particular cost function. So the Wasserstein distance between P and Q is like the minimum L2 cost of performing this optimal transport problem. So this, in fact, is a metric on the space of probability distributions. Now, let me tell you a very old fact that goes back to the 19th century about heat flow as a gradient flow. And then I will tell you a very new fact, which is only about 20 years old, about the heat equation, which was discovered surprisingly late in the context of its history. So this is the ordinary heat equation, which is, as we know and love. And a standard result is that the Dirichlet energy functional, which we can think of as the type of kinetic energy stored in P, it's just the gradient of P squared. This is known to be monotone under heat flow. Now, let me share a slightly stronger result that was known, I believe, since the 19th century. Suppose we consider the space of probability distributions in the following form. Suppose that we consider the space of smooth probability distributions, that is, distributions which are greater than or equal to 0 and which integrate to 1. And we let the tangent space, the space of probability distributions, be T sub P of dense of X. This is just how we'll denote it, which is the space of smooth eta which integrate to 0. Now, the point of this is that why should this be the tangent space, the space of probability distributions? Well, think of it the following way. If I take a probability distribution and I perturb it by a small amount, so suppose I look at P plus eta, the integral of P plus eta has to equal 1 due to the normalization, that P plus eta still has to be a probability distribution. But since the integral of P is equal to 1, and the integral of P plus eta also equals to 1, that means the integral of eta by itself has to equal 0. So that's an intuitive way of seeing why this is the right notion of tangent space on the space of probability distributions. So we're going to equip the tangent bundle of the space of probability distributions with the Riemannian metric, and we'll just associate it with the simple L2 inner product. So this is just an inner product on the tangent space, the space of probability distributions. And when we have a metric on a space, we can associate a gradient. So we can compute the gradient with respect to this L2 metric on the space of probability distributions of this Dirichlet energy functional. And a short computation shows that this is actually equal to minus the Laplacian of P. What this implies is that we can write the heat equation in the following form, that d by dt of P of xt is minus the gradient, the L2 gradient of the Dirichlet energy functional of P. So this establishes that heat flow is a gradient flow with respect to the Dirichlet energy, and in fact immediately implies that the Dirichlet energy is actually monotone under heat flow. In fact, it's monotonically decreasing, because maybe an intuitive way of saying this is that the kinetic energy, or the kinetic energy stored in P, is sort of being converted into heat energy. Or those are words that you could say. Anyway, this is an old result which was known since the 1800s. But now let me tell you a surprisingly new result, which was only known since circa 2001 due to the seminal work of Otto. This, what I'm about to tell you, is work which kind of revolutionized certain parts of PDE theory and probability, and has led to at least 1 or 2 Fields medals, depending on how you look at it, in terms of what are the implications and consequences of the fact that I'm about to tell you. So it has been known also since the 19th century that the differential entropy given here is also monotone under heat flow, that the entropy increases under heat flow. Now let's suppose we have a Riemannian metric on dense of X, and we're going to write down a rather peculiar looking Riemannian metric, where here the inner product between eta1 and eta2 elements of the tangent space is going to be equal to the right-hand side, where eta is related to eta bar by solving this differential equation. It can be established that this differential equation has a unique solution up to an additive constant. So eta bar is defined in terms of eta up to an additive constant, but that additive constant does not enter into the choice of inner product because of the gradient which acts on these eta bars. So this might look like a bit of a weird inner product, but in fact, it was established by Otto that this is surprisingly an infinitesimal version of the Wasserstein 2 distance that I told you before. So this Wasserstein 2 distance, if you reduce it to its infinitesimal form, namely for probability distributions which are very close to one another, then this in fact is the metric, the Riemannian metric, which gives rise to when you integrate it out to long distances to the Wasserstein 2 distance. So this is the infinitesimal version of the Wasserstein 2 distance, which has a Riemannian metric form. It has this kind of nice characterization. But here's the bit that's surprising. If you take the derivative with respect to the infinitesimal version of the Wasserstein 2 metric, if you take the gradient with respect to this metric on the differential entropy, you in this case get the Laplacian acting on P, which tells you that the heat equation, in fact, is a gradient flow with respect to the entropy, where the gradient is taken with respect to the Wasserstein 2 distance. So what this means is that it's not only the case that the differential entropy is monotone under heat flow, but in fact, the heat flow is completely governed by the gradient flow or by the gradients of the differential entropy with respect to the Wasserstein 2 distance. So in other words, it's not just that this is some ancillary quantity which happens to be monotone under the heat flow, but rather heat flow is completely governed by gradients of the entropy itself. So this is a pretty striking connection that ties together notions of information theory and ideas of entropy can also be done for Renyi entropies and other objects, but also the theory of optimal transport, and has been quite transformative in certain areas of PDE theory in the last 20 years. So now here's a flow of logic at the level of, say, syllogisms or the associative property or whatever you would like to call it. So the Polchinski equation we've seen at some high levels, a type of heat flow, or in particular, a type of infinite dimensional convection diffusion equation. I've also just argued to you that heat flow is a type of optimal transport gradient flow with respect to the entropy. So you might wonder at this very high level if the Polchinski equation is some form of optimal transport gradient flow with respect to a type of entropy. This is just at the level of words, but this should hopefully motivate why you would expect there to be a connection of the form that we will ultimately discover, that the Polchinski equation and more generally the Wegner-Morris flow equation can be understood as a type of optimal transport gradient flow with respect to an entropy. So let's now attempt to make this precise, or to make more precise statements about what actually is true. So first, we need to do a functional generalization of optimal transport. So suppose we have two initial and final, so we have an initial functional and a final functional, P1 of phi and P2 of phi, and we have a transport kernel, which is pi of phi 1, phi 2, which has an analogous marginalization property that it marginalizes to P1 on the first function, on the first functional index, and to P2 on the second functional index or coordinate, whatever you would like to call it. And we also have a cost function from the space of fields to the space of fields to R. So now we're interested in kind of the cost of transporting one field configuration, a probability distribution over field configurations to another probability distribution over field configurations.
Jordan, are we supposed to understand those path integrals as occurring in some particular scheme? That what's going on there?
No, these should be regarded as, so far, there's no, I haven't talked about what P sub lambda is yet. I'll introduce that into a slide as to how P sub lambda happens, but these
I just mean that the integral over phi I of pi, I mean, that's a path integral. So
Yes.
it's subject to the usual subtleties there. So
Yeah, so let's discuss this purely formally for the moment, and then you'll see why this is going to be better behaved. Just give me like one slide, and then I will come back to this. You'll see that it'll actually be better behaved for a particular reason that you'll see in like 30 seconds. So in other words, I understand that you're worried about whether any of these formulas are even sensible to write down, except purely formally. What does it even mean to perform this path integral? I'll address that in a moment. The thing that we actually really care about is minimizing over pi. So this is the cost function. This is the Kantorovich cost function. So it turns out that in our case, we're going to compute the Wasserstein-2 distance, where this is the analog of the Wasserstein-2 distance that we're going to be interested in right here. So this is like this distance between P1 and P2. And the point here, which actually makes this integral better behaved, is the following. It turns out that the kernel which is relevant is going to be the derivative of our cutoff function. Recall that our cutoff function was equal to 1 and then dips down to 0 at the cutoff scale. If you take the derivative of this with respect to lambda, then it's going to be some object which is localized only at the cutoff scale. So it's localized in a lump around p equals lambda. This is the object which appears in the ERG kernel. So in particular, this functional integral is actually only depending on degrees of freedom, which are localized near p equals lambda in momentum space. So a way of thinking about this intuitively is that the cost function that we're going to be interested in is one which only puts weight or cost on transfer and reconfiguring one field configuration into another, where the field configurations are localized near momentum scale lambda, but not near other places. So we're only going to be interested in doing this surgery or this optimal transport reorganization on field-theoretic degrees of freedom which are localized near momentum scale lambda, which also renders this path integral better defined because it's just a path integral over degrees of freedom which are localized in momentum space. Now, there is a formal question you could ask, not to, well, okay, I mean, maybe I'm running without being chased in the moment for what I'm about to say, but you could still ask about the nature of this optimization, because this is, of course, over a larger class of pi's than we actually know how to integrate over. But the point is that if we only know how to integrate over the pi's essentially in this regime around p equals lambda, then that's at least sufficient to do some form of the optimization, although, of course, the resulting pi that is a minimizer may not be a unique minimizer, but that will be okay for our purposes. So the ingredients that we require is a distribution of interest, p sub lambda of phi, some initial distribution which we wish to flow, and a background distribution, which for the moment, I will write suggestively this slightly peculiar choice, which is e to the -2 times the free action. And when I say the free action, I just mean the bare action for a free scalar field, which has the initial bare mass of the p sub lambda, which we're going to flow. At some initial scale lambda. And we also have a relative entropy. This is just a classical relative entropy between P and Q. And again, this in this particular sense, we have that C sub lambda dot is in fact the effective propagator, which indeed this is the term which localizes everything to around scale lambda. So the result is that this ends up being precisely equivalent to the Polchinski equation for this particular choice of Q. And we'll talk about why this choice of Q is interesting in a moment. Now, one thing that may have not been obvious is that when I showed you the Polchinski equation, I showed you the Wegner-Morris flow equation. They look extremely different from one another. That there's quite a bit of work to make the Wegner-Morris flow equation look like the Polchinski equation. Here is actually the connection between them. It's very simple when you write it in this way. Or sorry, let me make one conceptual comment first. What this equation shows us is that the renormalization group flow is a gradient flow with respect to the relative entropy. That's one interpretation of this equation. Anyway, so let me now connect this to the Wegner-Morris flow equation before I make some more comments on structural properties. Suppose we generalize the background distribution so that this is not the free action, but this is just some general, I'll call it S sub hat of lambda, which is called in the literature the seed action. It turns out that if you do this, then this now generalizes to the Wegner-Morris flow equation. So what's interesting is that we see that the relationship between the Polchinski equation and the Wegner-Morris flow equation is just having a more general choice of this background distribution, which is kind of an interesting structural observation because the equations otherwise don't look similar, but this is in fact how they're connected in retrospect. And I'll comment for a moment on what the heck this factor of 2 is doing here. But first, let me make some comments. There are some differences between what I've shown you in the finite dimensional heat flow setting. First of all, the Polchinski equation is a reaction diffusion equation, and the Wegner-Morris flow equation is even more general. So even at the kind of finite dimensional analogs of this, there's still work to do to get this all to hang together. There are subtleties with the space of probability functionals, which I've hinted at a little bit before. And there's also the importance of the positivity of the ERG kernel and its derivatives. So there are some interesting structural properties that, that for example, that you might want the theory which you're flowing to be a theory which corresponds to a unitary theory, or to not have some unstable potential or other pathologies, which there's some very minimal properties that you want of the action functional at the initial scale lambda for all of this to actually work. So let me give a quick example, which is the flow of a free theory. So let me go back for a second and just observe that in the Polchinski equation, that the background distribution was e to the -2 times the S sub lambda for a free theory. Okay, so let me go ahead. So in the Polchinski equation, it turns out that because of that factor of 2, that mysterious factor of 2, the flow equation actually simplifies. And it turns out that the RG flow in the Polchinski scheme of a free theory is simply the Wasserstein gradient of just the differential entropy of the free theory itself. In other words, for the free theory, this equation collapses the relative entropy into just the ordinary entropy. That's what that factor of 2 does in the Polchinski equation. In fact, the defining property of the Polchinski equation of that scheme is that it is in a certain sense the unique scheme in which the free theory flows according to its own entropy. That is a way of understanding what the Polchinski scheme is doing and how it should be specified. So what does the flow equation mean? So each step of RG flow, what we'll see in a few minutes is that each step of RG flow comes as close as it can to being a Wasserstein 2 geodesic while simultaneously maximizing the entropy production as much as possible. So a single step of RG flow actually wants to be a Wasserstein 2 geodesic, but also ends up having a penalty that it's also supposed to increase the entropy, or because of the way the minus signs works, decrease the relative entropy. Now, the relative entropy is needed since in general, the entropy, the ordinary entropy is ill-defined in the continuum. So if we have a discrete distribution, say P sub I, then the ordinary entropy, when we try to generalize it to the continuum, there's a dx which is sitting inside the log, basically for dimensional analysis reasons. So this is not so well defined, but if we instead consider the relative entropy between P and a background distribution Q, then this does generalize to the continuum setting in a nicer way. And if you wish, you can say that the dx's cancel in this ratio. So the choice of the RG scheme is also encoded in the choice of the background distribution Q and the ERG kernel. Maybe I'll go for another few minutes if that's okay, just to make a few more comments. That's all right.
Start in about 10 minutes.
Sounds good. So let me comment on RG monotones. So our RG equation suggests that something like the relative entropy is monotonic under RG flow. So it turns out that the right quantity to consider for a technical reason is that, I can explain why later if people are interested in the details, is that you look at the relative entropy and you subtract log of the normalization of this Q distribution. So this Q distribution is like e to the minus times some action divided by Z, and we want to basically slough off this Z term. Subtracting off a log ends up just killing this normalization inside the relative entropy. I can explain why this is the case. It has to do with a technical property of the way that the soft cutoff function works. But anyway, it can be shown using a formal argument that this quantity is monotone under these ERG flow equations of the Wegner-Morris type, including at least when I say define non-perturbatively, I mean formally using formal path integral arguments. And the proof of monotonicity relies on the positivity of a functional analog of what's called the Fisher information and some features of the ERG kernel. Now, there's some subtleties that arise about order of limits, but this can be handled. So this quantity, in some examples, we find that, well, m sub lambda well, this quantity, this you know, C theorem type quantity is often infinite, its derivatives often have meaningful finite parts. So for instance, in various examples in which we can compute this, even perturbatively, we find that this is proportional to a delta function at 0 times another function C1 of lambda. This delta function is from what you might call momentum space type contact terms, but it ends up being multiplicative, and the C1 of lambda term is finite. So to extract a finite RG monotone, or one that doesn't have this multiplicative renormalization, so one can show, you can just by staring at this equation, by the fact that this has to be greater than or equal to 0, the C1 of lambda has to be greater than or equal to 0. If we define a capital C1 of lambda as an antiderivative of C1, then it's the case that capital C1 of lambda is a finite RG monotone. So something, okay, well, I'll make a few more comments about this in a moment. Let's just do a few examples just to get a feeling for it. So we can compute this RG monotone exactly, being careful about orders of limits. It turns out that the quantity which is better behaved, I'm just going to skip ahead through it because there's something else I really want to tell you about before we conclude, that the derivative is better behaved. And it turns out that the derivative of this quantity ends up giving you something which is indeed can be, in a trivial way, is shown to be greater than or equal to 0 for all choices of cutoff schemes. For a scalar phi-4 theory, it turns out that a few loop computation shows you that if you do perturbative RG, you also find that that our statements about the monotonicity of this lambda quantity are also satisfied.
Can you say what this coefficient C1 is, or maybe it's antiderivative in terms of correlation functions? I'm a bit lost in the formulas. What is it about the scalar field theory that you were computing in a more invariant way?
We're essentially computing some type of regularized differential entropy for a free scalar field, or essentially a regularized.
You have some bunch of integrals of the K's, so it's just some correlator. I just can't tell which one it is. Right?
Oh.
Isn't the K like a 2-point function?
It's like a 2-point function. Yeah, that's right. It's like a 2-point function essentially. It's a 2-point function with a cutoff. Yeah. Sorry. Yes, that's right. So something maybe that you'll notice that is that, of course, a lot of these results are
just the 2-point function of the scalar. I'm confused. I thought that would probably not be an RG. What do you mean to say that that's an RG monotone?
So it turns out that in this particular case, in the Polchinski flow, which is not necessarily always the right choice of flow for these kinds of equations, K sub lambda of P squared is the effective propagator. So what this is the logarithmic derivative of K sub lambda with respect to lambda, and it's the integral over all momenta of this object. So if you will, it's the integral of the logarithmic derivative of the effective propagator. So it's like some kind of, that's literally what it is in this case. I mean, this is just a sanity check that this is not an interesting quantity. At least I don't see why this for a free scalar field is an interesting quantity. It's just to check that it's a sanity check to see that things are working.
I'm trying to understand if you're defining a new computable RG monotone for a general field theory or not.
It is for a general field theory. We just sort of follow this algorithm.
And what is it for a general field theory? Phrased in terms of the data of the field theory, like its correlators or things like, or partition functions.
Well, it's more like a partition function type object. It's a type of relative entropy between the probability functional at scale lambda and a background distribution, which corresponds to the scheme by which you are flowing. The fact
that you have to say background distribution makes me worried. Can you define it in a way that is scheme independent?
That's a great question. So I don't at the moment know, how do I say? The short answer is I don't at the moment know what is the right way of defining it in a scheme independent way. Although what I know is that due to some work that I don't have time to talk about at the moment by Morris and his collaborators, they understood that there is a large class of schemes that you can do in the Wegner-Morris flow equation, which essentially for certain kinds of quantities always give the same answer. So there's a vast number of schemes to which the Wegner-Morris flow equation corresponds. And there are certain subclasses of schemes for which they all essentially give the same answer for certain kinds of correlation functions or perhaps even entropies, like the ones that we're considering. So while I don't expect that there is something as general as scheme independence in the totality of the Wegner-Morris flow equation, I suspect that there are large families of schemes for which the answer that you find does not depend on that family of schemes.
Do you have a guess for what it is for a fixed point?
I suspect, let's put it this way. I suspect that there is a particular choice of scheme for a reason I can say about maybe in a few slides or at the very end, because I just want to talk about this variational thing and then I'll make some comments about this. I suspect that there's a particular choice of schemes or a set of schemes for which this result will reproduce, say for 2D theories, the ordinary C theorem. I can say why that's the case in a bit, but that's just a guess, and I can say why I believe that's true. But the short answer is that I don't know. So let me make a few comments about a variational formulation of RG, which is a variational formulation of gradient flow. So I'll just make a few comments on this and then I'll conclude. So suppose that we have an ordinary gradient flow of just some vector field. This is what a gradient flow looks like. If we discretize this into steps, into infinitesimal time steps of size tau, this is like a forward or a backwards derivative. We can characterize a single step of the gradient flow by a minimization problem. This is a well-known trick in numerics. That at step n+1 times tau, the argmin over x is equal to 1/2 tau times this distance plus this f, which is the f appearing in the gradient flow equation. So it turns out the application to the RG flow equation is as follows. Recall that I said that the Wegner-Morris flow equation tells us for this nice class of RG flows, if we start at some initial scale lambda naught and we flow by an amount t, then we can regard this as performing a reparameterization by some reparameterization tau and phi. This is the way in which the probability functional changes. So let me call p sub lambda of r of phi as the reparameterized version of p. Now we have a variational formulation of RG flow, where it turns out that there is a variational characterization of this reparameterization R, which implements a single step of RG flow. And what we see here is that we can obtain R by a minimum over the Wasserstein distance squared between P and as at our current scale in the reparameterized P, plus a penalty related to the relative entropy. So what this does is that we're kind of minimizing. So suppose we multiply both sides by 2 tau, or we multiply this by 2 tau, we're basically minimizing the Wasserstein 2 distance between the old P and the new P, namely the P that we're stepping towards, while paying a penalty related to the relative entropy. Now, the difficulty with this in practice is that this minimization requires 2 nested minimizations to compute, because the Wasserstein 2 distance requires an additional optimization to compute this in and of itself, because it's a minimization to compute W2. An alternative formulation is as follows. If f sub tau is a reparameterization, then the RG flow can be thought of as the push forward of so p sub lambda minus tau we can regard as a push forward as opposed to a reparameterization. So this is sort of like f sub tau is related to this R. It's like the inverse of R, if you will. It's just a different way of characterizing the reparameterizations of a probability distribution. And now we can write a variational formulation of RG flow where m is the Monge functional, where there's now only a single minimization out front. And the basic idea of this is that if you have sample access to p sub lambda, it's simple to sample with respect to the flow distribution. What you do is you first sample a phi from a p sub lambda, and then you map a phi to f sub tau phi under this this reparameterization that you've learned. Now I'll skip through this next. I'll just say what the point is. It turns out that this protocol has precisely the form that is amenable to what's called in the machine learning literature as stochastic gradient descent. There are efficient algorithms in order to find these f sub taus, which then actually give you efficient algorithms to perform a variational formulation of RG flow, where these f sub taus can be parameterized because if you have a translational invariant theory as a convolutional neural network, that this is some exact way, or rather this is some precise approximation scheme for being able to do a variational numerical RG flow. So let me make some few comments and I'll conclude. We've established that the Polchinski equation, more generally the Wegner-Morris flow equation, is the optimal transport gradient flow of a relative entropy. And moreover, that RG flow has a surprising information-theoretic formulation that involves optimal transport. We found new non-perturbative RG monotone, although what it means, and in particular its relationship to scheme dependence, is presently not so well characterized, or not characterized at all. And we've established that I just talked about a variational characterizations of RG flows, which is amenable to numerical methods. Now, there's some, as in terms of generalizations in future directions, it would be interesting to generalize to a richer class of field theories, say field theories with fermions and gauge fields. This is just a technical consideration. This was done in the context of the ordinary Polchinski or Wegner-Morris flow type equations by Morris and his collaborators in the first decade of the 2000s. I suspect that it should pretty straightforwardly adapt to the story that I told you today. Interesting possibility is to use the positivity of the monotone and the flexibility of our choice of RG scheme to constrain the signs of couplings in effective field theory. In other words, something that you might be able to do if you choose a particularly weird choice of scheme or something that would be slightly unnatural from the usual point of view of RG, but that still works with the formal properties of the ERG flow equations that I discussed, is that there appears to be some possibility in constraining various couplings in effective field theory using this positivity of this monotone that I was describing. But again, there's issues with anyway, there's still issues about scheme dependence even in that. There's questions about numerical methods for RG based on the sampling of the Wasserstein gradient flow. Maybe I'll skip over the CMERA interpretation. There's potential questions about what is the holographic interpretation. But finally, I would like to say that it would be interesting to really explore a further information theoretic understanding. In particular, there have been many papers that have been written, say, in the last 10 years about connections between renormalization group flow and the optimal transport, sorry, not optimal transport, but optimal transport has not been present, renormalization group flow and relative entropies, including some that connected in interesting ways to the C theorem. In particular, this paper by Balsubramanian, Heckman, and Maloney, which I think would be interesting to connect. Anyway, so with that in mind, thank you so much for your attention. I apologize for going over. Thanks.
Is there maybe any questions? I had maybe one question, Jordan. So if you wanted to actually, for example, at the end, try to put this on a computer, you're trying to do this over this space, this continuous infinite dimensional space of probability distributions. Aren't you gonna, again at the end, sort of make X sort of discrete, and then you have phi at different lattice points, and you're sort of doing kind of RG all over again in a sort of not so exact way? Is this what you meant by truncating at the end, maybe in the beginning of your talk?
Yeah, so the thing I didn't have a chance to talk about is, suppose that you do a lattice regularization of your field theory in the UV. Okay, so we have a lattice theory, and we're interested in seeing what that's flowing to. It turns out that this gives you, even within, so for there, if you have some initial Baire action, if you will, or Baire theory, you can sample field configurations via Monte Carlo sampling, as is usually done. The thing which is interesting here is that this gives you a very efficient algorithm to basically sample from the flowed version of that theory. So in other words, suppose that you suspect that this theory flows to something interesting in the IR. Okay, this in general is something which is hard to do in a numerically reliable way, especially if you have to do RG flow by a big amount and kind of control the errors that come from the fact that you're making approximations when you do your schemes. And I mean, I could talk about some more numerical, I'm maybe trying to say at the moment at a high level. The thing which is interesting is that this provides you, using some modern kind of neural net type techniques, a very efficient way of doing that kind of thing by using this alternative formulation of RG flow as a variational problem, as opposed to the way that people usually do it, where they just choose some particular way of coarse graining and try to see what happens with the theory. It just turns out that this is much more numerically efficient in principle. I'm not sure that addressed your question, but.
So if you take a two-dimensional theory, that's a sigma model with some target space metric, is there a nice interpretation for your relative entropy in terms of curvatures of your target space manifold, or?
That's a great question. The thing which I think gets closest to that kind of question is this paper, this 2014 paper, asks some related kinds of questions. And I have not yet connected it. I haven't really made an attempt to do so yet with the work that I told you today, although I suspect that it's closely connected. So I suspect that some answer to a version of your question lies in some synthesis between the work that I shared today and this 2014 paper here.
If there are other questions, let's thank the speaker again. Okay, great.
Jordan, that was fantastic.
Thank you. Thanks.
Do you mind a further question?
Please, yeah.
Good. Yeah. Good. In terms of your positivity,